This is the second module under the topic Building Blocks of Thermodynamics, and this is on control volume analysis. Let us start with the gas turbine engine, which is representative of an aircraft engine, and we have tried to show it schematically in this diagram. The outer shape looks like an aircraft engine, what we see under a commercial transport plane. Inside there are different devices or components, and we have identified them by some name. Essentially, we have air entering through what's called the intake of the engine, goes through a compressor, where it's raised to a higher pressure and temperature. Then there is fuel and heat addition in the combustor, followed by turbine, where it generates power to run the compressor, and then goes through a nozzle and out as a high-speed exhaust jet. We have discussed this in more detail in one of the previous lectures. The essential thing about a gas turbine engine is that it's a flow-through device. Which essentially means that at no point during the operation of such an engine that air is really stationary at any point. It continuously comes in, goes through the different parts of the engine and goes out. It's the high-speed jet going out is what is required to generate thrust in an aircraft engine. Okay, now if you were to analyze such an engine using thermodynamics, and we try to define a system, it turns out to be very difficult. Now imagine that we identify a mass of air that is entering into the engine, for example, this shaded region, and we call this our system, and we follow it through as it goes through compression, heat addition, and other processes. This mass of fluid, our system, goes through the compressor, combustor, turbine, and so on, and goes out. And as it does that, it's the property of the gas of the air changes, but it resides in different components at different times. It can also happen that there's a time when part of that system is in the combustor and the other part is in the compressor. Now, so one part is getting compressed, and the other part is getting heat addition, going through a heat addition. So what would we call that kind of a system, and what would be the process that we would call for the system? And there lies the difficulty in identifying the system. In fact, we will soon see that the properties of the gas is not uniform throughout this system that we have identified. If a part of it is in the compressor, it's a different pressure and temperature than the other part where fuel is getting burned and heat is being rapidly added into this. So the problem is, in simple terms, that we cannot identify a unique pressure, temperature, or for that matter of any thermodynamic property for a system that we would like to identify in this way to analyze our gas turbine. So we take a different approach, and that's called control volume approach. This is different from system approach in a way that we define a fixed volume in space. We identify a region in space which encloses a volume, and we say this is my fixed volume in space and this is my control volume. In this case, I have taken the control volume to encompass the entire engine. Whatever is inside the engine is part of my control volume. We have, as a system, just similar to a system, we have whatever is outside the control volume as surrounding, and the interface between the control volume and the surrounding is called the control surface, or the boundary in simple terms. And this is where again the important things are happening. Across a control surface, we have, as usual, heat and work interactions, which is energy exchange. In addition, we also have flow of gas coming in and out. So we also have mass exchange across the controlled surface. So we have to keep track of two things now, energy and mass. Once we do that, many of the things will fall into place and we should be able to analyze this engine. Now, a control volume is also sometimes called an open system. We will not use this nomenclature much, but just for reference, because a closed system was what we said of fixed mass. An open system has mass coming in and out. Both open and closed systems have energy exchange possible. Okay, a control volume can be of different shape and size, but it is fixed volume in space. It can, usually it is stationary, but it can also move around. So let's take another example of a control volume. Now I look inside the engine and identify what I call the compressor. It's this piece of machinery inside I'm showing as the compressor. Its job is to have a lot of rotating blades, and so that it's like a huge fan energizing in the air passing through it by increasing its pressure and temperature. So if I'm interested now in analyzing or calculating how the compressor works, I would place my control volume to encompass only the compressor. Is our control volume. And then worry about what kind of mass is going in and out of the control surface, what kind of energy interaction in the form of work and heat is going on. In this case, work interaction turns out to be very important. In fact, this shaft, that's part of this shaft that I've shown that connects the compressor to the turbine is a rotating shaft, and that drives a compressor. Essentially, we are saying that this shaft has a torque and forces give rise to work, as we know from simple Newtonian mechanics. And that work, in fact, we will soon define what's called a shaft work, is important, has to be accounted for, and that is what is raising the energy of the fluid inside. In fact, it's also changing the energy of the fluid from what pressure and temperature it's coming in to what it's going out of the compressor. And that we'll see that happens to be one of the major calculations we'll be doing in the class.